Let's get right into it. Number 7. White holes. Picture this. You're floating in space. Somewhere in front of you, there's a point, invisible, tiny, and from it, matter and light are blasting outward, not falling in, blasting out. Nothing can get close to it. Nothing can enter it. It just keeps pushing everything away. That object has a name, a white hole. You've probably heard of black holes. They pull everything in, including light. White holes are the mathematical opposite. Where a black hole only swallows, a white hole only spits out. It ejects matter and radiation at full force, creating a wall around itself that nothing can pass through going inward. Here's where it gets strange. White holes aren't science fiction. They come directly out of Einstein's equations of general relativity, the same equations that predicted black holes, which we've now seen with our own telescopes. The math is clean. White holes are a valid solution. The universe's rulebook allows them. So where are they? That's the uncomfortable part. We've never found one, and we have no idea if one has ever actually existed. They might be purely theoretical, objects that the math permits, but reality never built. Like a perfectly balanced pencil standing on its tip. Possible in theory, never seen in practice, but some physicists think white holes might be hiding right in front of us. One idea suggests that when a black hole eventually dies, and over unimaginably long stretches of time, they do die, it doesn't disappear quietly. Instead, it bounces, it transforms. The collapsed mass explodes back outward, and for a brief flash, a white hole exists where the black hole used to be. If that's true, then white holes have already occurred. We just weren't watching close enough for long enough. There's another angle that's even harder to sit with. Some physicists have suggested that the Big Bang itself, the moment everything in the universe erupted from a single point, behaved exactly like a white hole. An object that poured out matter and energy with nothing able to get back in. If that's right, then you're not just hearing about a strange theoretical object. You're living inside the aftermath of one. Number 6. Quark stars. When a massive star dies, it doesn't go gently. It collapses under its own weight in seconds and then explodes in one of the most violent events in the universe. What's left behind is usually a neutron star, a city-sized ball of matter so dense that a single teaspoon of it would weigh over 1 billion tons on Earth. But what if the collapse goes even further? Inside a neutron star, protons and electrons are crushed together so hard they merge into neutrons. That's why we call it a neutron star. The neutrons are packed together, touching, squeezed to the absolute limit. Now push harder, apply even more pressure. The neutrons themselves can't hold their shape. They break apart. And what's inside a neutron when you crack it open? Quarks, the most fundamental building blocks of matter we know of. A quark star is what you get when a neutron star collapses further, and instead of individual neutrons, you end up with a dense, continuous sea of free quarks, a form of matter called quark-gluon plasma, never seen naturally on Earth, existing at temperatures and pressures that break apart the particles we're made of. We haven't confirmed a quark star exists yet, but we found candidates. Neutron stars that are just slightly too small, slightly too cold, rotating slightly too fast to fully fit the neutron star model. Stars that sit in a gap between what we expect and what we observe. One of the most intriguing candidates was spotted in 2002. The object, called RxJ 1856.5-3754, was found to be significantly smaller than neutron star models predicted. Some researchers argued its size only made sense if quarks had separated and formed a denser state inside. Here's the detail that really sticks with you. If quark stars exist, the matter inside them has never existed in this form anywhere in the observable universe since the first microseconds after the Big Bang. For one brief moment, right after everything began, the entire universe was a sea of free quarks. Then it cooled, they combined, and the matter we know was born. A quark star would be a leftover of that first moment, a frozen relic from the birth of everything compressed into an object the size of a small city sitting silently in the dark between stars. Number 5. Thorne-Chetkov objects. Imagine two stars in a close orbit around each other. One is a red supergiant, enormous, bloated, a few hundred times wider than our sun. The other is a neutron star, tiny, incredibly dense, what's left after a star explodes and dies. These two objects spiral toward each other. The giant star's outer layers expand until the neutron star is no longer orbiting around it. It's inside it, swallowed whole, sinking toward the core. The result is called a Thorne-Zhitkov object, named after physicists Kip Thorne and Anna Zhitkov, who first described them in 1975. From the outside, it looks like any other large red star, but buried deep inside its core is a neutron star, spinning, radiating, eating the material around it. For decades, this was purely theoretical. Astronomers had no proof these objects actually formed. Then, in 2014, a team of astronomers announced they had found one, a star called HV 2112, in a nearby galaxy. Its light contained chemical fingerprints, specific elements in specific amounts that matched almost exactly what the models predicted for a star with a neutron star core. The scientific community was cautious. Debates followed. Some researchers questioned the interpretation of the data. The case is still not fully closed, but HV 2112 remains the strongest candidate we have. Here's the thing that's hard to shake. A Thorne-Zhitkov object is a star that swallowed another dead star and is being powered from the inside. It looks normal from a distance. There's no way to tell just by looking at it that there's a dense, city-sized remnant spinning at its center, slowly consuming everything around it. If they're real, and the math strongly suggests they are, there could be thousands of them scattered across our galaxy right now, looking like ordinary stars, hiding their secrets from every telescope we've ever built. Number 4. Dark matter halos. Every galaxy you've ever seen in a photograph, every spiral, every elliptical, every distant smudge of light is sitting inside something invisible. Not a cloud, not empty space, a structure, an enormous, roughly spherical region of matter surrounding the galaxy on all sides, extending far beyond the visible stars, holding the whole thing together. It has mass, it has gravity, and we cannot see it, touch it, or detect it directly with any instrument we currently have. These are called dark matter halos, and they're one of the most well-supported things in modern astrophysics, even though no one has ever directly observed one. Here's how we know they exist. When astronomers measure how fast stars orbit around the center of a galaxy, the outer stars should be moving slowly, the way the outer planets in our solar system orbit slower than the inner ones. That's just gravity. More mass at the center means faster orbits close in, slower ones far out. But that's not what we see. Stars at the edges of galaxies orbit just as fast, sometimes faster, than stars near the core. The only way the math works is if there's a massive, invisible structure surrounding the galaxy, a halo of matter that adds gravitational pull in all directions. This discovery was made by astronomer Vera Rubin in the 1970s. She spent years documenting what became known as the galaxy rotation problem. The numbers simply didn't add up without something invisible out there. The halos are enormous. The one surrounding our own Milky Way galaxy is estimated to extend about 1 million light-years from the galactic center. The visible part of the Milky Way, the disk of stars, the spiral arms, is about 100,000 light-years across. The halo is 10 times larger. We are inside it right now, moving through it, and we have no idea what it's made of. Physicists have proposed candidates, particles that don't interact with light, objects that emit nothing, remnants from the early universe. Experiments deep underground, in mountains in space, have been searching for decades. Nothing confirmed yet. Whatever dark matter is, it makes up roughly 27% of everything in the universe. All the atoms, all the stars, all the planets, everything you've ever seen or touched accounts for about 5%. The halos are real, we just don't know what they are. Number 3. Strange stars. There's a hypothesis in physics that sounds completely reasonable until you follow it to its conclusion. Then it becomes one of the most unsettling ideas in science. It's called the strange matter hypothesis, and it starts with quarks. Normal matter, protons, neutrons, atoms, is made of 2 types of quarks, up quarks and down quarks. But there's a third type, the strange quark, heavier, more exotic. And according to some theoretical models, if you combine roughly equal parts of all 3, up, down, and strange quarks, you get a form of matter called strange matter. The hypothesis, first proposed by physicist Edward Witten in 1984, suggests that strange matter might actually be the most stable form of matter in the universe, more stable than iron, which is currently the most stable normal element. If that's true, it would mean that under the right conditions, strange matter could convert ordinary matter into more strange matter on contact. A strange star would be an object made entirely of this material, denser than a neutron star, potentially more stable, a smooth, rigid surface made not of atoms but of a continuous fluid of quarks. Now here's the part that follows from this. If strange matter is more stable than normal matter, and if it converts what it touches, then a small fragment of strange matter, called a strangelet, landing on a planet made of ordinary matter would theoretically begin converting it. Atom by atom, the planet would be absorbed, transformed, piece by piece. Most physicists believe strangelets, if they exist, are too unstable to survive long in open space. The risk is considered low, but considered low is not the same as zero. Scientists at particle accelerators, including CERN, have specifically looked for strangelets in their experiments and found none. The absence is reassuring. But strange stars, if they exist, could occasionally shed small amounts of strange matter during collisions or explosions. And unlike most space threats, a strangelet wouldn't announce itself with light or radiation. It would arrive quietly, and the first sign would be that something had begun to change. Number 2. Primordial black holes. Black holes form when stars die. A massive star runs out of fuel, collapses under its own gravity, and if it's big enough, the collapse doesn't stop. A black hole is born. That's the standard story. But there's another kind of black hole. One that didn't need a star to form. One that might have been born before any star existed. These are called primordial black holes, and they would have formed in the first fraction of a second after the Big Bang. In those early moments, the universe was unimaginably hot and dense. Matter and energy were compressed together at scales we have no words for. The distribution of matter wasn't perfectly smooth. There were regions, tiny, random fluctuations in density, where matter was slightly more concentrated than elsewhere. In the chaos of those early moments, some of those high-density regions could have collapsed directly into black holes before atoms had even formed. The range of sizes is remarkable. Primordial black holes could be as small as an atom with the mass of a mountain, or as massive as tens of thousands of suns. There's no standard size. They would span an enormous range depending on when and how they formed. Here's what makes them important. One of the biggest unsolved problems in cosmology is explaining dark matter. Physicists have been searching for the particle responsible for dark matter for decades without success. Some researchers have proposed that primordial black holes, invisible, not made of normal matter, spread throughout the universe, could be the answer, or at least part of it. There's also a more personal connection to these objects. The supermassive black holes sitting at the centers of galaxies, including the one at the center of our own Milky Way, 4 million times the mass of our Sun, have long puzzled astronomers. They grew so large so quickly in the early universe that it's hard to explain through normal stellar evolution alone. Primordial black holes, already massive at birth, could have been the seeds. We have yet to directly detect one, but in 2020, a gravitational wave signal was detected from a black hole merger where one of the objects was significantly lighter than any known stellar black hole and heavier than any known neutron star. Some physicists immediately noted a primordial black hole would fit. The search is active, and the implications, if they're found, reach from the first moment of existence to the structure of every galaxy you've ever seen. Number 1. Cosmic strings. You've made it to the one that sits at the very edge of what physics can describe. The object that, if it exists, would be the oldest thing in the universe and one of the most powerful forces ever to move through space. Cosmic strings are not strings in the everyday sense. They're one-dimensional defects, cracks, in the fabric of space-time itself, left over from the very first moment the universe existed. Here's the idea. When the Big Bang happened, the universe went through a series of rapid cooling events, similar to how water freezes into ice. When water freezes, the ice crystals don't all align perfectly. Boundaries form between regions that froze in different directions. These boundaries are called defects. The same thing, according to some models of early universe physics, happened to the structure of space-time. As the universe cooled and the fundamental forces separated from one another, regions that settled into slightly different configurations left boundaries between them. Those boundaries are cosmic strings. They would have no thickness, thinner than a proton, but they could stretch for billions of light years, potentially spanning the entire observable universe, and they would be impossibly dense. A single inch of cosmic string would weigh roughly 10 million billion tons. An object with that mass and that geometry would bend space-time around it. Anything passing close to a cosmic string would be pulled toward it. Two images of the same distant object would appear on opposite sides of it because light would curve around both edges. This lensing effect is actually one of the ways astronomers are searching for them. The tension inside a cosmic string, the energy pulling along its length, would be comparable to the force that held the early universe together. If a loop of cosmic string formed and began to shrink, it would oscillate at near the speed of light, radiating gravitational waves, ripples in space-time, of an intensity that modern detectors are only just beginning to be able to look for. We have not confirmed a cosmic string exists, but the search has become urgent. Gravitational wave detectors like LIGO and the pulsar timing array have begun detecting signals that some researchers believe could only come from a network of cosmic strings vibrating across the universe. If that signal is confirmed, it won't just be the discovery of a new object. It will be direct evidence of a crack in the structure of reality, a scar left in the fabric of the universe from the moment everything began, a thread connecting us to the first instant of existence. That's it for today. Subscribe for more.